So that was an example of using an angle that's in standard position on an xy plane and figuring out its trig ratios. But let's look at angles that could be greater than 90 degrees. And to do this, we'll use our exact values that we got for our special angles in the previous lesson. So we're going to start with this question: what is the exact value of the sine of 135 degrees? So before we start, we need to draw on our grid 135 degrees. So of course we always start with our initial arm right here on the x-axis, and now we're going to draw a terminal arm that creates an angle of 135 degrees. So starting from here, I'm going to move upwards around, and it's going to get to here, which is 90 degrees. So how much further do I need to go to get to 135 degrees? Well, 90 plus 45 more gets me to 135. So 45 more gets me to approximately halfway, or exactly halfway between this this part right here and this part right here. So halfway through quadrant 2. And I'm going to draw a terminal arm right here. So we know this angle right there is 135 degrees. Now I want to find the sine of this angle. So of course I could go on my calculator and just hit sine of 135, and but what will happen is I'll get a decimal answer. And I want the exact value, not a decimal answer. But what I'm going to show you here is a neat little trick. If I come up with just some random point P on this terminal arm, let's say we'll put it right there. And again, I'm going to draw down a triangle to the x-axis. So I'll use that dotted line down there. And this is a right angle triangle here. We get this angle that when our angle is in standard position over here, we used theta. So I don't want to use the same letter. I'm going to use this letter to represent this angle that I find in between here. It's not an angle in standard position, but it's what we're going to call a reference angle. I'm going to use this letter beta. So beta is another Greek letter that is used for unknown things, and you often see it in trigonometry to represent a second unknown angle if you've already used theta. So I'm going to use beta, and beta is going to represent this angle that we have in between this side of the x-axis. It's not the initial arm, but this side of the x-axis and the terminal arm. Beta again is going to be called our reference angle, and we can determine what beta equals for this question because we know that all the way around to here would be 180 degrees, but we only want 135, so beta is equal to 45 degrees. Now the question is, do I know what the sine of 45 degrees is? Well, of course we do. We memorize the special angles and the special triangles, and if I quickly just draw the one that uses 45 degrees over here, remember it's an isosceles triangle, sides 1, 1, and root 2, and each of these angles are 45 degrees. So the sine of 45 degrees is opposite over hypotenuse, or 1 over root 2, which when we rationalize it is equal to root 2 over 2. Well, it turns out that beta, being 45 degrees, has a trig ratio of root 2 over 2. And I'll get my calculator back out here, and I forget what root 2 over 2 is as a decimal. So let me see here. Root 2, turn on here. So root 2 over 2 as a decimal is equal to 0.707. So let me just write this here. Well, it turns out that if I go on my calculator and I try to figure out the sine of 135 degrees, so let's put that in here, the sine of 135 degrees, it also equals 0.707. It's in fact the exact same ratio. So what does this tell me? Well, this tells me that the related angle here, or the reference angle beta, is going to give me the same sine ratio as 135 degrees. Both of them are going to be the same. And as we see here, it's root 2 over 2, as is an exact answer. Well, I wonder if that works for other trig ratios as well. So this was for the sine of 135 degrees. Let's try another one. And before we do that, though, let's just cover a couple definitions here. So some of the things that I've said, we can use the Greek letter beta, so this little b, to represent what we call the reference angle. So this is the angle that isn't the angle in standard position, so this isn't theta. Our theta for that previous question was 135 degrees. That's the angle in standard position. But our beta represents the angle that is between the terminal arm and the x-axis. We say that 135 degrees, or the sine of 135 degrees, is related to the sine of 45 degrees since they both share the same reference angle. Both of them would have 45 degrees as its reference angle. And so then they both equal root 2 over 2. So we're going to see if we can try this for cosine of 135 down here. So again, let's draw where 150 degrees would be. So we're going to start from my initial arm. I'm going to draw 150 degrees over. So first of all, I get to 90, and then I need to go 60 more. So 60 more is 2/3 of the way over. And I'm going to get a terminal arm that would go start here and go right through here. So this is equal to 150 degrees. So what is the measurement of beta, or what is the measurement of my reference angle? Well, how much is left over when I come down here? And it might help to just draw yourself a little dot here. It doesn't matter, somewhere on that terminal arm. Draw a little line that comes down to the x-axis. And this is my beta in there. Beta is going to be equal to 150, or 180 minus 150, which is 30 degrees. So the question now is, if beta is my reference angle, what is the cosine of my reference angle, or the cosine of 30? This will probably help me out. Well, let's get our special triangle over here, the one that has 30 degrees. So remember, 30 floats to the top, 60 floats to the bottom, or sinks to the bottom. And we start with 1 on the bottom, 2 on the hypotenuse, and root 3 on the left side. So cosine is adjacent over hypotenuse, or root 3 over 2. And to just verify that we're on the right track, I'm going to figure out what root 3 over 2 is on my calculator. So let's bring my calculator back out. And I'm going to calculate root 3 over 2. So square root of 3 divided by 2. That equals 0.866. So let's now figure out, if my reference angle has a ratio of 0.866, what the cosine of 150 is. If it uses the same pattern as sine, hopefully it's the exact same ratio here. So let's plug in here cosine of 150, and I should get the exact same thing. The number is exactly the same, but look out front. There's a negative sign there. So the cosine of 150 actually equals negative 0.866, or we can say that's negative root 3 over 2. The ratio is the same, but for some reason it's a negative. I wonder if that's an anomaly. So is that only for cosine? What about tangent? So I'm going to do one more example here, tan of 120, and see if we get the same result. Is it going to be positive, or is it going to be negative? So tan of 120, again, I'll quickly draw a sketch here of where our terminal arm will be. So I'm going to start here. It's going to go to 90 degrees plus an extra 30 more. So that's my terminal arm right there. So if I have a point on here and I go drop down to the x-axis, my beta here is, if this is 120 degrees, my beta here is going to be 60 degrees. So let's figure out the tan of 60, because that's my reference angle. Well, we already have this triangle out here, so remember tan is opposite over adjacent, so root 3 over 1, or just equal to root 3. Well, let's get our calculator out here. What is root 3 as a decimal, just to verify for us? So square root of 3, 1.732. So this equals 1.732. So let's check out tan of 120. Our guess here is that it's going to be it's going to involve root 3. It should be the exact same ratio, just like the other two, they're the same ratio, but I don't know if it's positive or negative. So let's check on our calculator. So tan of 120, negative 1.732. So it turns out that the sine ratio was the exact same, the same sine and everything. So negative root 3 right here, or negative 1.732. Turns out that sine was positive, but cosine and tangent were both negative. So I don't want to just guess. Is that going to be true all the time, or just for those angles, or whatnot? Well, we do have a way to figure out whether or not the answer will be positive or negative. We know for sure it'll be the exact same ratio, but do we know if it'll be positive or negative? And it's something called the cast rule. How the cast rule works is, if we see on our XY grid here, I've written out the letters C, A, S, and T, and each letter has its own quadrant. Quadrant 1 has the letter A, Quadrant 2 has the letter S, Quadrant 3 has T, and Quadrant 4 has C. And what this little diagram tells us is, if our terminal arm falls in each of those quadrants, then that particular trig ratio happens to be positive. The other trig ratios are negative. So in our previous 3 examples, all 3 of those questions ended up being in quadrant 2. We had an angle of 120 degrees, an angle of 135 degrees, and an angle of 150. All 3 fall into quadrant 2. And that is the S quadrant. So the sine ratio was positive, but the cosine and the tangent ratios were both negative. If we had angles that were in quadrant 3, so I don't know, think of an angle that is in quadrant 3, the angle would have to be somewhere between 180 degrees, because 180 degrees is right here, and 270 degrees. So let's say it was 200 degrees. So any trig ratio to 200 degrees, tangent would be positive, but both sine and cosine would be negative. And if we were in quadrant 4, so anything between 270 degrees and 360 degrees, the cosine ratio would be positive, but sine and tangent would both be negative. I'll let you decide or figure out what the A stands for. We've seen many examples where angles were in the first quadrant. So hopefully you realize A stands for all. So in this case, all of the trig ratios are positive in quadrant 1. So A stands for all. Okay, so now that we know this cast rule, it should be pretty easy to figure out what the exact ratios are. So let's find the exact value for the tan of 330. So first of all, I'll use this grid up here to help me out. So let's assume that I have an initial arm right on the positive side of the x-axis, just like before. And my terminal arm is needing to make an angle of 330 degrees. So I would go all the way to 90, I would go all the way to 180, I would go all the way to 270, and 330 would be in my fourth quadrant. So it would actually be somewhere probably out there. My 330 degree angle would start from here and come all the way around to here. That's 330 degrees. That's my angle in standard position. And my beta, or my reference angle, is the leftover bit right here. So we can find this by doing 360 degrees minus the 330. That's right there. So this beta here is 30 degrees. 30 is going to be my reference angle. Notice how I always do the reference angle up to the x-axis. So over in the second quadrant, came down to the x-axis and figured out the reference angle. Over here, I came up to the x-axis. If we were in the first quadrant, I would come down to the x-axis. If I was in the third quadrant, I would go up to the x-axis. It's always relative to the x-axis, not the y-axis. That is very important. So our beta here, or our reference angle, is 30. So what is the exact value of the tan of 30 degrees? Well, get out your special triangles again. So I'll quickly draw one here. Dun, dun, dun. Remember, 30 floats to the top. I have 1, 2, root 3. So tan of 30, opposite over adjacent, 1 over root 3. And when I rationalize, this is just equal to root 3 over 3. So if I know tan 30 is root 3 over 3, my 330 degrees should be the same ratio, but is it positive or negative? Well, in quadrant 4, because my terminal arm's in quadrant 4, only the cosine ratio is positive. So I know that tan of 330 is going to be the same ratio, but it's going to be negative. So this is negative root 3 over 3. And it's that easy. So let's just quickly do a couple more examples. So I've written the special triangles at the top just to help us out. So let's start with 210 degrees. I'm going to find the sine, cosine, and tangent of 210 degrees. So of course our first step, let's draw out where our terminal arm will be. So I know 210 degrees is after 180, so it's in fact 30 degrees after 180. So it would end up going out here. My angle in standard position goes from here all the way around. That's 210 degrees. But my beta is just the little part from the x-axis down to the terminal arm. So that little bit there, if I know this is 180 degrees to here, is going to be equal to 30. So my reference angle is equal to 30 degrees for this question. So what is the sine of 30? Well, using my special triangles here, I look at 30. 30 is right here. Sine is opposite over hypotenuse, so 1 over 2. So I know sine of 30 is 1 over 2. But, so that's my reference angle. My actual angle of 210 is in quadrant 3. And using the cast rule, I know that C, A, S, and T, only the tangent ratio is positive in quadrant 3. So my sine ratio has to be negative. So the sine of 210 degrees, negative 1/2. What about the cosine? So cosine of 30 degrees, because 30 degrees is my reference angle. Well, I look up here, adjacent over hypotenuse, root 3 over 2. Again, only tangent's positive in this one, so the cosine of 210 degrees, well, it's going to end up being negative root 3 over 2 because we're in quadrant 3. And last but not least, tangent of 30 degrees. I can just do this in my head now. Tangent of 30 degrees is opposite over hypotenuse, opposite over adjacent, 1 over root 3, which turns into root 3 over 3. And because I'm in quadrant 3, tangent's positive. So tan of 210 degrees is going to equal the tan of 30 degrees, which was root 3 over 3. The second example down here, 315 degrees. I'll just quickly talk about it. 315 degrees is after 270 but before 360, so it's in fact halfway between those two in quadrant 4. So I know in quadrant 4 only the cosine ratio is going to be positive. And I'm using the 45 degree triangle because my beta is 45 degrees if the rest of my angle here is 315. So sine of 45 degrees, 1 over root 2. I'm in quadrant 4, so that means that it has to be negative. So the sine of 315 is just equal, I can write it as the negative value of the sine of 45 because I'm in quadrant 4, negative 1 over root 2. Negative 1 over root 2. Cosine of 315. Cosine of 45 is 1 over root 2. I'm in the fourth quadrant, so my ratio is going to be positive. So cosine of 315 is going to be positive 1 over root 2. And tangent of 45 degrees is 1 over 1. And because I'm in quadrant 4, tangent is negative. So tangent of 315 is just negative 1. Pretty simple stuff. So I leave you with an example. I want you to try this example and bring your solution to this example to class tomorrow. There will be other questions for you to try during your homework. Of course, the homework is already posted on your unit outline, and if you don't have a copy of the unit outline, you can download a copy from our class calendar. And our homework is also posted on the class calendar under today's lesson. So read this example to yourself. See if you can follow the diagram. If you're having trouble with it, there is an example just like it in your textbook in this chapter. So please try this before you come to class, and we will see you there, and I'll talk to you later in our next lesson. See you there.